dear STEM students in pre-calculus. And I'm your teacher, Mrs. Beverly Nevado, your teacher in your specialization subject. Today's lesson is all about the sigma notation, in which you are expected to achieve with the following learning competencies. First, you are going to know the uses of sigma notation to represent a series. And last, applies the use of sigma notation in finding the sums. So find comfortable place so you can properly listen and study. Get ready your notebook, pen, and learning activity sheets, and be ready to jot down the key points in our lesson. First, let us define the sigma notation. Sigma notation refers to provides a short and convenient way of writing long sums. For example, 1 plus 2 plus 3 plus 4 plus 5 plus up to plus 15. And it can be written using the capital Greek letter sigma. Did you know that Leonhard Euler was a Swiss mathematician and physicist who made fundamental contributions to countless areas of mathematics, was the first to use summation notation? This can be written using capital Greek letter sigma, as you seen on the given example. The sigma notation represents the sum of all the terms between x is equals to 1 and 15. In general, sigma notation is in this given form. This form is read as the summation of expression from x is equals to lower to upper. In this notation, the limits of a sum of the lower and upper bound or limits are written above and below the sigma, and describe the range to be used in the series calculation. The lower bound has the form of variable is equals to integer, and the upper bound is usually a large integer. The variable is the index. It changes based on the expression. Expression or summand of the summation is usually some formula involving the variable. To illustrate how we write a sigma notation, let's evaluate the following examples. Example number 1. Directions. Expand each summation and simplify if possible. The summation of 3x minus 1 from x is equals to 1 to 4. To solve, we substitute the range of values from x is equals to 1 to 4 to the expression and add the results. Is equals to 3 times 1 minus 1 plus 3 times 2 minus 1 plus 3 times 3 minus 1 plus 3 times 4 minus 1 is equals to 3 times 1 is equals to 3 minus 1 plus 3 times 2 is 6 minus 1 plus 3 times 3 is 9 minus 1 plus 3 times 4 is 12 minus 1 is equals to 3 minus 1 is 2 plus 6 minus 1 is 5 plus 9 minus 1 is 8 plus 12 minus 1 is 11. And add, the answer is 26. Example number 2. Directions. Expand each summation and simplify if possible. The summation of 4 raised to I from I is equals to 0 to 5. To solve, we substitute the range of values from I is equals to 0 to 5. Is equals to 4 raised to 0 plus 4 raised to 1 plus 4 raised to 2 plus 4 raised to 3 plus 4 raised to 4 plus 4 raised to 5 is equals to 4 raised to 0 is 1 plus 4 raised to 1 is 4 plus 4 raised to 2 is 16 plus 4 raised to 3 is 64 plus 4 raised to 4 is 256 plus 4 raised to 5 is 1024. Then add is equals to 1365. Example number 3. Directions. Write each expression in sigma notation. 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus up to plus 1 over 100. To solve, let's observe the pattern of the terms. Each term takes the form of 1 over n. The numerator of each term is 1, and denominator takes the values of the variable. In sigma notation, we could write this as the summation of 1 over n from n is equals to 1 to 100. Example number 4. Directions. Write each expression in sigma notation. -1 plus 2 minus 3 plus 4 minus 5 plus 6 minus 7 plus 8 plus up to plus 20. To solve, let's observe the terms. The sign repeatedly changed from negative to positive, but the terms is increasing by 1. Thus, we can conclude that each term is affected by -1 raised to n. If n is odd number, the sign is negative. If n is even, the sign is positive. In sigma notation, we could write this as the summation of -1 raised to n times n from n is equals to 1 to 20. Let's proceed to the second keynotes, the properties of sigma notation. We will prove 4 properties of summation. These properties will allow us to evaluate formulas containing sigma notation more easily and allow us to derive equivalent formulas. Property 1. The expression is a constant c. The summation of c from I is equals to m to n is equals to c times n minus m plus 1. In derivation of this formula, the summation of c from I is equals to m to n is equals to c plus c plus c plus up to plus c is equal to c times n minus m plus 1. For example, simplify the summation of 2 from I is equals to 2 to 4 is equals to 2 plus 2 plus 2 is equals to 6. By applying the property 1, the summation of c from I is equals to m to n is equals to c times n minus m plus 1 is equals to the summation of 2 from I is equals to 2 to 4 is equals to the constant c is equals to 2 times the value of the n is 4 minus the value of the m is 2 plus 1 is equals to 2 times 4 minus 2 plus 1 is 3. The answer is 6. There is a special case for property 1. This is applicable for problems where the variable starts at 1. The summation of c from I is equals to 1 to n is equals to the c times n. For example, simplify the summation of 2 from I is equals to 1 to 4 is equals to 2 plus 2 plus 2 plus 2 is equals to 8. Using the special case of property, the summation of c from I is equals to 1 to n is equals to c times n is equals to the summation of 2 from I is equals to 1 to 4 is equals to 2 times the value of the n is 4 is equals to 8. Let's proceed to property 2. Coefficient c of an expression is a real number. The summation of c of f of I from I is equals to m to n is equals to c times the summation of f of I from I is equals to m to n. In derivation of the formula, the summation of c of f of I from I is equals to m to n is equals to c times f of m plus c times f of m plus 1 plus c times f of m plus 2 plus up to c of f of n. Observe that c is a common factor in all the terms of the expression. Thus, we factor out c is equals to c times f of m plus f of m plus 1 plus f of m plus 2 plus up to plus f of n. Therefore, the summation of c of f of I from I is equals to m to n is equals to c times f of I from I is equals to m to n. To clearly understand, let's look at this given example. Evaluate the summation below. The summation of 2i from I is equals to 1 to 5. To solve, we substitute the range of values from I is equals to 1 to 5. Is equals to 2 times 1 plus 2 times 2 plus 2 times 3 plus 2 times 4 plus 2 times 5. Is equals to 2 times 1 is 2 plus 2 times 2 is 4 plus 2 times 3 is 6 plus 2 times 4 is 8 plus 2 times 5 is 10 is equals to 30. By applying the property 2, let's have C times the summation of f of I from I is equals to n is equals to 2 times the summation of I from I is equals to 1 to 5 is equals to 2 times 1 plus 2 plus 3 plus 4 plus 5 is equals to 2 times 15. The answer is 30. The terms of the series are similar with arithmetic sequence, with a common difference of 2. Thus, we can use S is equals to n times n plus 1 over 2 to evaluate the summation of I from I is equals to 1 to n. Therefore, 2 times the summation of I from I is equals to 1 to 5. We are going to substitute the value of n is equals to 5. 2 times 5 plus 1 over 2 is equals to 2 times 5 times 6 over 2 is equals to 2 times 5 times 6 is 30 divided by 2 is equals to 2 times 30 divided by 2 is 15 is equals to 30. We have the special case of property 2. If the expression is a variable and the lower bound is 1, the summation of I from I is equals to 1 to n is equals to n times n plus 1 over 2. Property 3. The summand contains two or more expressions. The summation of f of I plus g of I from I is equals to m to n is equals to the summation of f of I from I is equals to m to n plus the summation of g of I from I is equals to m to n. If the summation is composed of two or more expressions, the summation of f of I plus g of I from I is equals to m is equals to f of m plus g of m plus f of m plus 1 plus g of m plus 1 plus up to plus f of n plus g of n is equals to, combining like terms, f of m plus f of n plus 1 plus up to f of n plus g of m plus g of m plus 1 plus up to plus g of n is equals to the summation of f of I plus g of I from I is equals to m to n is equals to the summation of f of I from I is equals to m to n plus the summation of g of I from I is equals to m to n. Let us have the given example. Simplify. The summation of 4i plus 2 from I is equals to 1 to 3. To solve, we substitute the value of I from 1 to 3 is equals to 4 times 1 plus 2 plus 4 times 2 plus 2 plus 4 times 3 plus 2 is equals to 4 times 1 is 4 plus 2 plus 4 times 2 is 8 plus 2 plus 4 times 3 is 12 plus 2 is equals to 4 plus 2 is 6 plus 8 plus 2 is 10 plus 12 plus 2 is 14, and the answer is 30. Using property 3, the summation of 4i plus 2 from I is equals to 1 to 3 is equals to the summation of 4i from I is equals to 1 to 3 plus the summation of 2 from I is equals to 1 to 3. To evaluate the summation, we can use property 2 and 1. Therefore, it is equals to 4 times the summation of I from I is equals to 1 to 3 plus the summation of 2 from I is equals to 1 to 3 is equals to 4 times 1 plus 2 plus 3 plus 2 times 3 is equals to 4 times 6 plus 2 times 3 is 6 is equals to 4 times 6 is 24 plus 6 and the answer is 30. Property 4. Telescoping sum. The summation of f of I plus 1 minus f of I from I is equals to n is equals to f of n plus 1 minus f of n. To derive this formula, the summation of f of I plus 1 minus f of I from I is equals to m to n is equals to f of m plus 1 minus f of m plus f of m plus 2 minus f of m plus 1 plus f of m plus 3 minus f of m plus 2 plus up to f of n plus 1 minus f of n. Note that the terms of f of m plus 1, f of m plus 2, f of m plus 3, up to f of n all cancel out. Hence, we have the summation of f of I plus 1 minus f of I from I is equals to m to n is equals to f of n plus 1 minus f of m. To understand, let us have the given example. Let's simplify. The summation of 1 over I minus 1 over I plus 1 from I is equals to 1 to 4. To solve, let's substitute the value of I is equals to 1 to 4. Is equals to negative times the summation of 1 over I plus 1 minus 1 over I from I is equals to 1 to 4 is equals to negative times 1 over 1 plus 1 minus 1 over 1 plus 1 over 2 plus 1 minus 1 over 2 plus 1 over 3 plus 1 minus 1 over 3 plus 1 over 4 plus 1 minus 1 over 4. By simplifying, is equals to negative times 1 over 1 plus 1 is 2 minus 1 plus 1 over 2 plus 1 is 3 minus 1 over 2 plus 1 over 3 plus 1 is 4 minus 1 over 3 plus 1 over 4 plus 1 is 5 minus 1 over 4 is equals to negative times 1 over 2 minus 1 plus 1 over 3 minus 1 over 2 plus 1 over 4 minus 1 over 3 plus 1 over 5 minus 1 over 4 is equals to negative times negative 1 plus 1 over 5 is equals to negative 1 plus 1 over 5 is negative 4 over 5 multiplied by negative 1 is equals to 4 over 5. Using telescoping sum, the summation of 1 over I minus 1 over I plus 1 from I is equals to 1 to 4 is equals to negative times the summation of 1 over I minus 1 over I plus 1 from I is equals to 1 to 4 is equals to negative times 1 over 4 plus 1 minus 1 is equals to negative times 1 over 4 plus 1 is 5 minus 1 is equals to negative times 1 over 5 minus 1 is negative 4 over 5. And the answer is 4 over 5. Let us have the derived formula using telescoping sum for evaluating sum of powers of integers. First, the summation of I squared from I is equals to 1 to n is equals to n times n plus 1 times 2n plus 1 over 6. The second, the summation of I raised to 3 from I is equals to 1 to n is equals to n raised to 2 times n plus 1 squared over 4. The third, the summation of I raised to 4 from I is equals to 1 to n is equals to n times n plus 1 times 2n plus 1 times 3n squared plus 3n minus 1 over 30. The last, the summation of I raised to 5 from I is equals to 1 to n is equals to n raised to 2 times n plus 1 squared times 2n squared plus 2n minus 1 over 12. Let us have the given example. Let's simplify. The summation of I raised to 3 minus 2I raised to 2 from I is equals to 1 to 3. To solve, let's use the property 3 and property 2. The summation of I raised to 3 from I is equals to 1 to 3 minus 2 times the summation of I raised to 2 from I is equals to 1 to 3 Let's substitute the value of I from 1 to 3 is equals to 1 raised to 3 plus 2 raised to 3 plus 3 raised to 3 minus 2 times 1 raised to 2 plus 2 raised to 2 plus 3 raised to 2 is equals to 1 raised to 3 is 1 plus 2 raised to 3 is 8 plus 3 raised to 3 is 27 minus 2 times 1 raised to 2 is 1, 2 raised to 2 is 4 plus 3 raised to 2 is 9 is equals to 1 plus 8 plus 27 is 36 minus 2 times 1 plus 4 plus 9 is 14 is equals to 36 minus 2 times 14 is 28 and the answer is 8. Using the derived formula, the summation of I raised to 3 minus 2I raised to 2 from I is equals to 1 to 3 is equals to, from the summation of I raised to 3 from I is equals to 1 to 3 minus 2 times the summation of I raised to 2 from I is equals to 1 to 3 is equals to n squared times n plus 1 squared over 4 minus 2 times n plus 1 times 2n plus 1 over 6. By substituting n is equals to 3 to the formulas, the summation of I raised to 3 minus 2I squared from I is equals to 1 to 3 is equals to the summation of I raised to 3 from I is equals to 1 to 3 minus 2 times the summation of I raised to 2 from I is equals to 1 to 3 is equals to n raised to 2 times n plus 1 raised to 2 over 4 minus 2 times n plus 1 times 2n plus 1 over 6 is equals to 3 raised to 2 times 3 plus 1 squared over 4 minus 2 times 3 plus 1 times 2 times 3 plus 1 over 6 is equals to 3 squared is 9 times 3 plus 1 is 4 squared over 4 minus 2 times 3 plus 1 is 4 times 2 times 3 is 6 plus 1 is 7 over 6 is equals to 9 times 4 squared is 16 over 4 minus 2 times 3 times 4 times 7 is 84 over 6 is equals to 9 times 16 over 4 is 36 minus 2 times 84 over 6 is 2 times 14 is equals to 36 minus 2 times 14 is 28 is equals to 8. Note that the formulas can only be used if and only if the lower limit is 1. Thank you for watching.